Hi guys, my name's Ben and today you'll be joining me on Fox Academy, your go-to resource when cramming for your test tomorrow. Organic compounds review is our lesson for today, and I know you guys are used to seeing my face on the big screen, but this chapter is focused heavily on visuals and diagrams, so diagrams will be used instead of my face. So firstly guys, I'm going to go over a little overview of what I think will be on your test and the key concepts to make sure you fully understand organic chemistry. So, the unit being focused primarily on drawing and naming functional groups, so we're going to make sure that you're amazing at doing both. The functional groups in this video that we'll be covering are alkenes, alkalides, alkenes, alkynes, ethers, alcohols, esters, amines, ketones, aldehydes, amides, carboxylic acids, benzenes, and hydrocarbons. I'm also going to be making sure that you thoroughly understand priorities when naming, the reactions to form some of these functional groups, and as well as multi-step reactions. Firstly, I'm going to go over a few must-know definitions, such as organic chemistry, which is the study of carbon and molecular compounds that are building blocks of life, and functional groups, which are any group or a group of atoms or organization of bonds determined by specific properties of an organic molecule, so things such as solubility and polarity. So the first thing that we're going to start with is priority nomenclature. Priority nomenclature isn't something conceptual. There is no definite reason why each suffix represents a different rank in the hierarchy of naming. It is something that the IUPAC decided would make the naming process easier, and although we haven't yet gone over all of the functional groups on this list, it is a general rule of thumb on the order in which compounds are named. So here guys, we just have a quick list of all of the things that we call main chains. So this is how you name your main chain. If it's one carbon, it would be meth and then your suffix, or 3 would be prop and then your suffix. Just something to know before we hop into the next part. So starting basic, we're going to make sure that you can effectively name and draw alkanes. Alkanes are hydrocarbons. That means that they are molecules that contain only C and H atoms. When naming alkanes, as well as most other functional groups, the main chain is the base of the name and determined by the amount of C atoms present for the suffix. An ane is added. For example, heptane, 7 carbons, 1, 2, 3, 4, 5, 6, 7 carbons, and then the suffix ane is added because it's an alkane. So, alkyl groups can also be added to functional groups, which are carbon atoms formed off the branch of the main chain of a hydrocarbon, so they name with the same prefixes as we learned earlier, but end with YL, and they are the numbered from the side to the least carbons before it. So this here would be an alkyl group, and it would be methyl, and you can see that it's attached to the second carbon. So, now that we understand the basics of naming and drawing, I'm going to move a little quicker into the remaining ones, assuming that you know how the alkyls work and finding the longest carbon chain. So, moving on to alkalides, essentially just alkanes with one or more H molecules bonded to a carbon replaced with a halogen. So halogens are more electronegative than hydrogen and carbon, so they make the molecule more polar, increasing the strength of intermolecular forces that lead to high boiling points. So here, in this case, is bromine is bonded to the second carbon, meaning that it would have the prefix bromo because the O is replaced at the end of bromine and it's attached to the second carbon, which is why the second is here. And then it ends with ane, just like alkanes do. So moving on to alkenes. Alkenes are a group of atoms within the molecule that determine the properties of the molecule. So they affect solubility, melting point, boiling point, and chemical reactivity. Multiple bonds are considered functional groups because they add to the properties of the molecule, change them. So alkenes are more reactive than alkanes and less stable because of the multiple carbon bonds. So, basically, they're just alkanes with a triple bonded carbon instead of their suffix is -ine instead of -ane, and the triple bond is specified by a number showing on which carbon it is. So for the example here, 1-butene, the 1 is showing that it's attached at the first carbon is the triple bond, and the ene is added because it's an alkene. And naming would be vice versa. So if you were given this picture here, and you saw that it's on this carbon here, between 1 and 2, you would have the 1, and then the ene is for the alkene. Alkenes, on the other hand, have the same characteristics and properties of alkenes, but have a double bond instead of a triple bond, so they use the suffix -ene instead of -ine when naming. For example, 3-methyl pentyl 2-ene has a double bond on the second carbon and a methyl on the third, so its name is drawn like so. The place of the double bond is kind of sandwiched in between this number right here, between the suffix and -ene. So here we can see that it's attached in between the second and third, and then there's a methyl group on the third, and that would be an alkene. Moving on to ethers, an organic compound containing an oxygen atom between two carbon atoms in a chain. Properties of ethers include boiling point, higher than similar-sized alkanes, but lower than similar-sized alcohols because of intramolecular forces. But alkyl groups make them more nonpolar. So when naming, identify the two alkyl groups, write the name of the shorter group with oxy, then the longer alkyl group as if it were an alkane, and add the number if attached somewhere else in the chain. So here we have 1-ethoxybutane, and we can see that the shorter chain clearly is ethyl, and you add oxy because it's the shorter chain, making it ethoxy, and then we have butane, which is 4 carbons over here, and it's attached on the first carbon, the O. So alcohols are organic compounds that contain a hydroxyl group, a functional group that has the properties arranged on the depending of the carbons. So there's 3 types of alcohols depending on the different arrangements of the carbons. There's primary alcohols, where it is where the hydroxyl group is bonded to a direct carbon atom. There's a secondary alcohol where the hydroxyl group is bonded to a carbon atom with 2 alkyl groups bonded to it. And there's a tertiary alcohol where the hydroxyl group is bonded to a carbon atom with 3 alkyl groups bonded to it. So this is an example of a primary alcohol. This is a secondary. And this is a tertiary. So when naming alcohols, the lowest number is assigned to the carbon atom with the hydroxyl group. For example, butan-2-ol, as shown here, is written because it is butane, replaced with ol at the end, and the 2 is sandwiched in between because that's the carbon that the hydroxyl group is bonded to. So when writing the names of alcohols, the same steps are used as if you're given the picture here. You count the amount of carbons, you know that it's butane, use the prefix, add the suffix ol, and then sandwich, as I like to say, in between which carbon it's on. Moving on to esters, which are organic compounds that contain a carboxyl group bonded to a second O2 atom, which is bonded to another carbon atom. When naming alkyl portions of the alcohol name on the first one, then add ic acid on the end of the carboxylic acid to replace with O8, in this case providing a double bond that the O gives to the suffix O8 and then bonded to another O. So here we have ethyl propanoate. So we know that ethyl has 2 carbons and then is bonded to an O. And then we know that propane, which is 3, is double bonded to the O, so that's why it gets the O8. So moving on to ketones and aldehydes. Ketones are an organic molecule containing a carboxyl group that is bonded to at least 1 carbon atom, so it's located at the beginning or the end of the chain. This means that you replace the final E with al, and no position is needed because it's always on the first carbon. So here we have butanal, which you see the carbon is double bonded to the O on the first carbon, so there's no need to name anything, and that's how you can tell it's an aldehyde. Now, moving on to ketones. Ketones are organic molecules with a carbonyl group that is bonded to at least 2 carbon atoms, so it's found somewhere within the chain. So to name, replace the final E with -one and the lowest possible number assigned to the carbonyl group's position. So here, butanone would actually be written buta, and then you determine where the carbon is. So it's on the second carbon is where the O is double bonded to one. And that's how you know that it's a ketone, because it's not located on the edge, it's located in between 2 carboxyl groups. And then here we just have a little chart that you'll be using somewhere in your homework that helps you compare and contrast aldehydes and ketones. So moving on to amines. Amines are organic compounds that relate to ammonia, which is NH3, and that contain a nitrogen atom bonded to 1 or more alkyl groups on each atom. So there's 3 different types of amines, like there are alcohols. There's primary amines, which are nitrogen groups attached to 1 alkyl group. There are secondary amines, which are attached to 2 alkyl groups, and there are tertiary amines, which are attached to 3 alkyl groups. So, in order to name primaries, remove the E from the alkane and add amine, and a secondary tertiary name is based on a larger alkyl group, so write the other shorter alkyl group in front with N to indicate additional attachments. So here we have an example of a primary amine, 1-propamine, and you could see that the nitrogen is attached to the first carbon, giving it the name amine because it's only attached to one alkyl group, whereas secondary amines, such as N-methylpropamine, are attached on one side to a propyl group, giving it the name propamine. But then remember, in front we had to put N, and then the smaller group, methyl 1, attached to the first carbon, propamine. So in total we have N, which is where the carbon is, and then it's the methyl, which is the smaller alkyl group, 1, which is the carbon it's bonded to, and then propamine, which is the longer strand, which is these carbons here. Now we have amides, which are organic compounds that contain a carbonyl group bonded to an N atom that are also similar to esters and are joined by an N instead of O. So to name, the first part of the amine and then the second part from the carboxylic acid ending with amide. Just like naming esters, but with naming an amine instead of an alcohol and adding N with the amine group. So here we have 1-ethylbutanamide. Sorry, my head kind of cuts it off a little bit. So it's written like this, 1-ethylbutanamide. And you can see that the O is double bonded to this carbon strand, which is 4, which is the butanamide. And then on a side strand, we have ethyl. And the N is bonded to the C, which is also bonded to the double O, making it an amide. Moving on to carboxylic acids, there are weak organic acids containing at least one carboxyl group. So carboxyl groups are a carbon atom that is double bonded to one O2 and single bonded to an OH group. So to name, you replace the E at the end of whatever alkene you have and add oic acid. So the number of atoms from the carboxyl group, and add di or tri if there are more carboxyl groups. In our example here, we have pentanoic acid, which only has one carboxyl group at the end here. And you can see that it's double bonded to an O and single bonded to an OH. So instead of being pentane, you move the E, add oic acid because there's 5 carbons. Benzene is the final and most interesting group that we're going to be talking about today. With always changing amount of bonds, benzene is the only group that can bond 1.5 times, so it fluctuates between 1 and 2 bonds very fast. So to name, add benzene if it is just a suffix for a main chain, such as shown here. So here we have pentene, but we have a benzene added, so the suffix becomes benzene. Here, for the second part, we have, if it is a side group, it's added as a prefix, and it's called a phenol. So see how we have here pentane, and then we are adding our group on top as a phenyl group. And then if it is attached to an OH group, like shown here, it's called a phenol. Now we're going to go on to some of the type of the reactions. There are some of these located in your textbook if you're looking for actual questions, and there are some of the worksheets because we're running out of time. So here we have substitution reactions, which are the replacement of an atom or compound of a reaction, and they can form things like alkyl halides. There's complete combustion reactions, which is when a reaction such as an alkane reacts with an O2, releasing a CO2, H2O, and thermal energy. There are hydration reactions, which is the addition of H2O to a compound, resulting in an OH group being formed, called an alcohol. There are dehydration reactions, which is a reaction that involves the removal of an H atom and a hydroxyl group from the reactant, producing a slightly smaller molecule, and water forms an alkene from an alcohol. And there's things like mild oxidization, which is the loss or gain of electrons when using an alcohol and yields an aldehyde or a ketone, depending if it's primary or secondary. And then there's lastly esterification, which is the reaction of a carboxylic acid and an alcohol to form an ester and water. Alright guys, we're back with our last example, which is our multi-step example and probably our most important one. So we're going to start with an alkene, 4-methyl-2-pentene, to make 4-methyl-2-pentanol, and then oxidizing it to make it 4-methyl-2-pentanone. So we're going to start with 2-methyl-2-pentene, as shown here on the second carbon. There is a double bond, making it an ene. And then on the fourth, there's a methyl group as shown here. And then we're adding water, as you do in a hydration reaction, with the catalyst of H2SO4 to make 4-methyl-2-pentanol. So you can see here on the second carbon, we now have an OH group On the fourth, we still have our methyl, but it's now broken the double bond, taken on an oxygen, and become an alcohol. The next step would then be to mildly oxidize this alcohol to get our final results here. So we have our 4-methyl 2-pentanol, as shown above here. This is the same, I just brought it down for you guys. So it's 5 carbons. On the fourth, there's a methyl, and on the second, there's an OH group. And then we're mildly oxidizing it, exposing it to air, giving us 4-methyl 2-pentanone. So as you can see here, there's now a double bonded O. It's given up one of its H's, and there's still a methyl group attached on the fourth. So you can see that it's lost now a hydrogen, and it's now double bonded to this O over here, making it a ketone. So hi, thank you guys for watching. This little bit at the end isn't part of the video. This is kind of just like a little farewell talk I'm having with you, Miss Willand. So it's been a pleasure spending half of my grade 12 year with you, Miss Willand. I really wish you and your family the best in the future, and can hope that you continue to passionately teach students for many years to come, and that you keep science fun and interesting for them. I just want to say that it's been a really fun semester, and you've kept me engaged in biology and chemistry, and I thank you so much for that. So one last time, this has been your host, Ben, signing off.